Yep, recording has been started. So welcome aboard. I will immediately go into sharing screen. And today what we've got to do is first examples. And then I would like to prove a very important though boring lemma about basis of the absolute cone algebra. Okay, so but let's start with examples. Of course, examples of, oops, I moved something, sorry. Examples of, again, I moved something, sorry. Of the relative cone path algebras. Okay, so one example is extremely elementary. We can ask the following question: what happens if you have a graph with no edges? So E1 is the empty set. Well, then we have the following situation: whether we take the path algebra of this graph, or you see here all vertices are sinks because no vertex emits any edge. So consequently, there are no regular vertices. So the only thing we can do is to divide by this first Kunstkrieger relation because there are no regular vertices. But because there are no edges, in fact, this ideal is empty. But when you take into account the first Kunstkrieger relation, so the path algebra is just equal to the cone algebra, and this is equal to the Levi path algebra. And as you know, this is equal to all finitely supported functions from the set of vertices into the graph. Okay, so this is a commutative algebra. I understand that this is completely clear because for starters, when there are no edges, then the extended graph is equal to the graph. And when there are no edges, then there are no relations whatsoever. Relations that define the cone algebra, cone path algebra, or Levi path algebra, these relations are non-existent because all they involve edges, which are not present here. And when you look at vertices alone, then all that you have is the path algebra of this graph, which is just a cloud of disconnected dots. And we know that the path algebra of such a thing is nothing but the pointwise multiplication algebra of all finitely supported functions from E0, a set of all vertices into K. All right? And obviously, this algebra is uniform if and only if E0 is finite. Now, let's do something more interesting. And actually, it turned out to be far more involved than I expected. So I'll try to do it step by step. You see, you shouldn't think that I'm actually proving what I'm going to say right now. In order to prove that these examples are what I claim them to be, you need to have a basis theorem. And we'll prove this basis theorem. We'll start with basis theorem today. Then we'll finish, I don't know, next week maybe. So it will be your exercise for the forthcoming recitation classes to prove that indeed these examples are what I claim them to be. Okay, but let's, I think it's very important after you have a general definition to study various examples to get at least some basic intuition as to what these creatures are. Okay, so let our graph be a very simple graph, which is basically a path. So I have a vertex V1, a vertex V2, dot, 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 and I go up to vertex Vn. Okay, so this is my graph. It has n vertices and n minus 1 edges. Okay, and I choose x to be a subset of all regular vertices. So it's a subset of the set V1 dot, dot, dot up to Vn minus 1. Okay, because Vn is not a regular vertex, it is a sink. So x is a subset here. All right. And we ask the following question: what is the relative to X concav algebra of this graph. And I claim, and this is what one of you will prove in verification class, but this is a sort of matrix algebra, which I denote like this. So these are n by n matrices over a field, but well, not quite. This X modifies it. Okay, then let me explain what this letter symbol stands for. So here, MNXK is the modification of the matrix algebra. The standard matrix algebra of n by n matrices of our field K, whose all of diagonal entries are unchanged. So I'm not modifying off diagonal entries. All the diagonal entries labeled by I such that VI, when I take the vertex VI, then this vertex is not, it does not belong to the set X cup Vn. Well, I don't know. I'm just touching something and the screen moves. Sorry about this. Okay, so I modify only entries on the diagonal labeled by an index I, which has this property that the vertex with this index does not belong to the set X cup Vn. So this is not a regular vertex at which we do modification. This is a regular vertex at which we do not impose second conjugate relations. Okay. Because remember the definition of relative concav algebra, X is the set of all regular vertices at which we impose the second conjugate relation. Okay, so we take a vertex VI, which is a regular vertex, and at which we do not impose such a relation. So that's the meaning of this notation. So I could also write it alternatively as regular vertices of E less X. Okay, I'm going to put if and only if, and now where's eraser? It's here. Okay. This is if and only if X is a regular vertex that is not in X. Okay, that's an alternative description. I wrote X, I'm sorry, I meant VI. VI. Well, this is in parentheses, this is just a remark. And what I do at this entry, so all these entries, diagonal entries labeled by such an I, are changed to the unital commutative ring, because it used to be a field everywhere, right? If you have the usual matrix algebra, MNK, every entry is just our ground field. Okay, and now on the diagonal, but only at this spot labeled by I's, such that VI satisfies this property, my ground field is changed to the unital commutative ring. Let me label it as K2. I take polynomials in one variable, but I divide by the relation x squared minus x. So x is an idempotent, okay? So this is a two-dimensional algebra over K, and that's what we have in each slot I, such that the I is a regular vertex that is not in X. Okay? And I have to finish, and all other diagonal entries are unchanged. We'll do a concrete example in a second, but let me finish the definition. Now I have to say how I do multiplication. Of course, this is a matrix algebra, so I multiply by the usual matrix multiplication formula. But now some of these entries are no longer fields. So in order to make sense of the multiplication, I have to specify what happens in certain places. So the multiplication of entries, because once I have multiplication of entries, I have multiplication in my matrix algebra. I take Aij and Bjk, and I put some big dot here to denote this special multiplication I'm defining. These are entries in MNXK. I hope I did it correctly before. Yes. For the special case of I equal to J or J equal to K, so in other words, we're multiplying two entries, but with the assumption that one of these entries is on the diagonal. Okay, so it's on the diagonal. It might be either in the field, in which case we know what to do, or it might be in this commutative ring, in which case I have to tell you what to do. So this is induced in the natural way by the field structure of K. In other words, I'm doing nothing, I'm just multiplying the field. If this I or J happen to be an index at which we do not do the modification. Sorry, at which we do modification. So for instance, an element of X or the sink. So then it's just the field structure of K, which is multiplication. But otherwise, I have to take into account the ring structure. Of K2. So imagine that I have, say, I equal to J and J equal to K. All right, so I'm multiplying AII by BII. And assume that BI is a vertex such that it is a regular vertex which is not in X. So I do not impose my second constraint relations. So I do have this funny unital two-dimensional commutative algebra. And then I just multiply in this algebra. Okay, so this is what I mean by using the ring structure of the algebra structure of K2. But that's not enough, because it might also happen that one of these entries is in the ring and the other entry is in the field. So we have to specify in what sense our ground field is a bimodule over this commutative ring. And it has a very simple structure. This is a symmetric bimodule structure. K2 bimodal structure, yeah, of K given by the character of K2 sending x to 1. Now let me make a digression. Let me explain. So whenever you have an R module, an R bimodule, okay. So I have an action from the left, say by half of R on M. And I have a ring homomorphism, say from S to R. So I can, so-called change of base, I can make M natural into an S module simply by saying that S acting on M is by definition F of S times M. Okay. So this is one principle. Okay, so it particularly works for symmetric bimodules of a commutative rings. And what is a character? A character is a homomorphism. A character of an algebra is a homomorphism into the ground field. Okay, so if I have a K algebra A, and I have a homomorphism, say chi from A to K, this is called a character. So here, what we are looking at this algebra K2 and the character from K2 to K. And remember that I'm just taking polynomial as one variable, and I divide by this ideal generated by x squared minus x. But it's obvious that then the evaluation map, both at x equal to 0 and at x equal to 1 works, because 0 squared is equal to 0 and because 1 squared is equal to 0. Okay. So I have two characters, evaluation at 0 and evaluation at 1. So here I'm taking this character evaluation at 1. And this is my ring homomorphism, which turns my field K into a symmetric K2 bimodule. All right. So in other words, if I have anything in my field K, some, I don't know, beta, and I multiply it by x, then x beta is just beta. Right. So x behaves as the unit of the ring when acting on the field, yeah, because of the way we define the bimodal structure. And now we are home and dry. Everything is specified because well, almost, almost. So I know where things are modified. Okay, maybe it's also a good moment to make a comment. So here is my matrix, and everywhere off diagonal, I just have my field K, nothing more. And here, at some places I have K, at some places I have K2, at some places I have K, at some places I have K2. Okay, depending on the label. But because Vn is a sink, here I always have K. So that's not negotiable. At the last slot, I always have a field. Right? So this is how things are modified. And now imagine that I take this matrix multiplication, Aij times Bjk, right? So what happens? Well, when I is different from j and simultaneously j is different from k, I'm multiplying two things which are off diagonal. All right. So I'm taking a number, I multiply by number, and I land, and surprise, surprise, I might land in the field, but I might also land in the ring K2. So so I also have to specify what happens from multiplication of all diagonal entries. What I explained so far is what happens when one of these entries is diagonal. Okay. And if one of the entries is diagonal and it is at this diagonal slot where it is just a field, then nothing happens. I multiply in the usual way. When it happens that this is in my ring K2, all right, and then I multiply. I have to use this bimodal structure. to multiply a field by an element from K2, and this is what I just explained. And finally, if it happens that both of these entries are on the diagonal, and they happen to be at the slots at which I have this modified entry, which means I have a ring K2 instead of a field K, but I simply use the ring multiplication. Okay, so that's the recipe, and I hope I didn't screw it up. Yeah, because then the only case that we're interested in when I want both entries on diagonal, and I is equal to j, and then j is equal to k, and then everything is just equal to I, right? So then I'm multiplying in one and the same entry, okay? Because what I was worried about, I cannot multiply the things from different entries on the diagonal. It should be multiplied to 0, but it's enforced by the matrix multiplication. Okay, so to end the story, you see, so now we also need to explain how we multiply off-diagonal entries. Okay, so because you see, this is for this assumption that I is equal to j or j is equal to k. So now we have an assumption that both of them are different. So I is different than j and j is different than k. All right. So that's the last case to consider. So for I not equal to j and j not equal to k, so this is our standing assumption now. This multiplication is given by the following formula. I have Aij dot Bjk, and I have to basically consider two cases. If I have Vi, which is at the slot at which we do not enforce the second configuration, so it does not belong to the set X cap Vn. So in other words, it is a regular vertex which is not in X. Then I have a final result of this multiplication. So I multiply these two numbers, because remember, these are numbers, because this is in the field and this is in the field, because they are off diagonal. But surprise, surprise, multiplying two elements in the field need not result in an element of the field. And in fact, when we have this situation, okay, that Vi satisfies this property, and I is equal to k, and I is less than j, all right, then we have Aij times Bji, right? Because I'm taking I equal to k equal to I. So it's Aij Bji, but these are just numbers which are multiplied, but then I multiply it by this second generator. This special generator X is non-trivial idempotent in my ring, in my algebra K2. Okay, so this is what I obtained over here, and otherwise this is just multiplication of numbers. So Aij times Bjk otherwise. Yes, I'm wondering what happens if J is no, I have to have k equal to I. Yeah, I think I missed one case, so maybe let me still write Aij Bji. I keep these two things as before. But now doesn't make sense for me to take J less than I. No. This is yeah. Okay, sorry. Luckily, this is wrong. Yeah, that's the whole thing. Yeah, I mean, you see, I just did my computations at home to verify it, but actually to prove it rigorously, you must have a basis, a linear basis. Otherwise, this is just hand waving. But I want you to know what you're supposed to prove. Okay, so this is the result. I just defined for you what I mean by this relative matrix algebra issues. Okay. And I repeat, this is the usual matrix algebra, except that it has some entries of diagonal modified, and multiplication of entries is modified as I already explained. I don't want to repeat it. I will just show a concrete example. So first, in particular, when you take X to be the set of all regular vertices, okay? So let me write it down. In particular, if I take the Levitt path algebra of this graph E, then this is indeed the matrix algebra. Okay? Because you see, when do we get the Levitt? We get Levitt when X is all regular vertices. When X is all regular vertices, then this set is E0. These are all vertices, which means that this condition is vacuous. This never happens. Yeah, so first possibility drops out. And also, if you look at the places where you do modifications, well, again, you do modifications at the empty sets. So you don't do any modifications. So all entries are just the field, okay? And you have the usual matrix modification. Right? The entries labeled by I start with blah, blah, blah. So, but if X does not depend to the set of, if VI does not depend to the set of all vertices, there is simply no such I. Okay? So nothing is modified, no entry. So here you have K all the way through, right? So that's what you've got in particular. But now maybe let's do a 2x2 case, which is easy to write down. So now take E to be just given by two vertices and one edge, okay? So V1, V2. And let's take, yeah, I want to consider, I'll just consider the Kohn algebra, all right? So my X is the empty set, all right? X is the empty set. So I have one regular vertex V1. And at the regular vertex V1, I do not impose the second constructor relation, right? So by writing Vi is not in X cup, Vn, it means that Vi is equal to V1. Because Vn is equal to V2, and Vi not belonging to this one element and V2 means just Vi equal to V1, okay? So for I equal 1, I do some modification. I have something different. So my matrix algebra looks like this. Here I have my ring K2. Here I have my field K, and my field K. All right. So this is my M2 empty set E. Okay. So I know how we multiply. So let's see. Let's see now in practice how this multiplication looks like. So here I'm taking simply some. Maybe let's do it on the next page. I have some alpha plus beta x. All right. And here I have mu gamma. Okay, so all these Greek letters are numbers. And now I multiply by alpha prime plus beta prime x, mu prime, gamma prime. Okay, so this is the usual matrix multiplication. So when I multiply these two entries, the top left corner, then this is multiplication in the ring. Okay, so I have alpha prime plus, and now remember that x squared is equal to x. So I will have here alpha beta prime plus beta alpha prime plus beta prime x. Okay, so that's my first entry. Now my second entry, and now remember the rule. So now this is multiplying mu with mu prime. They are both off a diagonal, and they do not satisfy. Well, I mean this will be just as. Yeah, sorry, I should have added it here. Because this is just result of multiplying this with that. Oops. But I also have to multiply mu with mu prime. Okay. So this is plus mu prime. Okay. So that part is in the field, and that part is the coefficient next to my non-trivial idempotent in the ring K2. Okay. So now we multiply this by a plus beta x times mu prime. But remember, here's the rule that I use this character sending x to 1. So this is basically nothing else but alpha plus beta times mu prime. Okay. And then I have simply mu gamma prime. So plus mu gamma prime. And this is a number, as it should. You see, this is in K2, and this is a number. Okay, let's go on. Here I have mu times this element in the field. So this is mu, sorry. So it's mu times alpha prime plus beta prime. Again, I use this symmetric bimodal structure. So I put x to 1 when I multiply an element in the field. And I have just gamma mu prime. And it works because you should have something in the field, and you do get something in the field. Okay, and then now finally, you just have what? It's mu times mu prime plus gamma prime. And again, it's in the field. Okay. So that's an example how this complicated rule works in practice. One bad thing which this example doesn't show is when you get E star, and I'm just wondering. Whether I did it correctly. Okay, let's check it. So if I denote this edge between V and V2 by E, the idea, general idea for Levi-Pav algebra is that what you have here have V1, here have V2, and here you have E, and here have E star, right? And in the usual Levi-Pav algebra, well, you do have, of course, you have E star E equal to V2, but you also have E star equal to V1. And this is precisely this one relation which is missing in the cone algebra. So when I do such a multiplication, let me just take the same thing, V1, V2, E star. So when I okay, so so that's why because this is not equal to V1, okay, I have to basically do the following. I have also here plus E star. I have the second idempotent, okay, here, plus E star. This is what gives me this two-dimensional ring. And yeah, so one in this two-dimensional case, I guess the problem is that you never really have a situation in which you get E star. Yeah, because there's no way I don't get E star, because the only time I multiply star and E is in the opposite order. But I guess if we go to a more complicated case, say imagine that we have 3 by 3 matrix. Okay, and now I have also an F, and all I want is just say an example that I have. Yeah, but I have say here 0 E 0. Okay, say 0 everywhere else. And here, say I have also 0 E star 0. Okay, so I multiply this. So the only non-trivial entry, all right, will be in the middle of a diagonal, but this will be E star. Okay, and if I choose my X to be the empty set, okay, so I don't do modifications at V2 because V2 is again a regular vertex, then this is not equal to V2. All right, and that's why I have, so I did everything correctly, just that this was too simple example. If you take 3 vertices and 3 by 3 matrices, then you have this funny effect. Okay, then you have this funny effect that when you multiply things, and you see this works because this is an entry A12. So I'm multiplying A12 times B21. Okay, so I have this I less than J, and I have K equal to I. You see, so that's exactly the case. Like this, and then when I multiply it, well, I don't get a number. I get something. This is my X. This is my idempotent. Okay. So I just wanted to explain to you how I got the idea for such a crazy multiplication. I didn't have a wild dream. I just computed it like this. But this is more heuristic, and if you really want to do rigorous, well, this will be an exercise having a basis here. Okay, you can nicely hook up an isomorphism between these algebras. But I suppose this description is not so bad, right? I mean, we say that this is a certain relative matrix algebra. Let me write it more nicely. Yeah, okay. This is N. Where it's basically a matrix algebra, but with some slots modified and some multiplication modified ever so slight. Okay. So I think that's enough for this example. Really, what is most important, your take-home message, is that this in particular, this is very important. This is very important. That when you take the Levitt path algebra of such a path, simple path graph, then this is full matrix algebra. So this is a big advantage of path algebras. Perhaps you remember that if you take the path algebra of such a one-path graph, then you get only upper triangular matrices. So that's the upshot of doing the Levitt path algebras, because you get these full matrices. So in particular, you can have it to be a sister algebra, which was impossible for path algebra. So, and you can see where it comes from, because what I'm doing, I'm adding these ghost edges. I'm taking the path algebra of the extended graph, and then I divide by relations. Okay. But in particular, in order really to prove this isomorphism, you must have a basis theorem. There's no way around it. I mean, you can just see that there is some homomorphism, but you have to prove injectivity, and you cannot do it without knowing what the basis of the Levitt path algebra is. And this will be a major theorem we're about to prove in the forthcoming time. Okay, so that's, I guess I explained this example. So let me now continue and go with another example. So example number 3. This will be simpler. Don't panic. This was the most complicated example. Now my graph is going to be just one loop. By the way, do you have any questions about this matrix example? No, I don't hear any questions. So let's take just one loop graph. Okay, so I cannot have my x is obviously I either take Levitt or Cohn, right? Either I take I have just one regular vertex, so either I impose at this regular vertex the second conspirator relation, or I don't. Okay, there is no in between. Okay, so if I take the Cohn case, so CK of E, well, then it's obvious. Here you don't need to prove anything. It's just by definition. You take the path algebra of extended graph, but this will be just a non-commutative polynomial in two variables. And this first conspirator relation which you impose is precisely x, y equal to 1. And that's it. And this is known as the Tetris polynomial algebra. Okay, so this is what happens when you take the Cohn algebra, and what happens when you take the Levitt path algebra. Well, then you impose both conspirator relations. So not only xy equals to 1, but also yx equals to 1. Okay. So LK of E is just the Laurent polynomial algebra. But let me comment. These are very simple examples. We have nothing to prove here. Just enjoy it. But why are these examples so important? Well, nobody can stop me from taking K to be the field of complex numbers. I can just introduce the star structure, saying, okay, it's a star algebra with x star equal to y and y star equal to x. All right. And then what you realize, you will get the algebra where you have a star algebra where you have just one generator, call it S, and it satisfies S star S equal to 1. That's exactly a recipe for isometry. And now if you take the C-star completion of this algebra, say the universal completion, there's a lot of work of Coburn, who actually prove that the universal completion is isomorphic with just the bounded operator algebra given by unilateral shifts on the Hilbert space. Well, you get this beautiful sister algebra, okay, generated by universal isometry. It has a very concrete realization. You can as I just said, you can take the Hilbert space to be, say, square summable sequences, natural numbers. You can take your orthogonal basis EI, with I being a natural number, and then the S is just a unilateral shift. SEI is EI plus 1. And you can very quickly see that S star S is equal to identity. Well, because if I shift up and shift down, that's the identity. However, SS star is not identity. It's identity everywhere except for I equal to 0, right? Because if I have S star on E0, this is 0. So SS star E0 is still 0. Okay, so it's not 1. It's simply a projection. If you want it in a matrix form, SS star is just the identity matrix, but S, so this is S star S, but SS star is the projection which has 0 here and 1 everywhere else in there. And this is an extremely important sister algebra. Okay, this is denoted by T for Teplitz. So the Teplitz sister algebra is extremely important. For instance, Kunz, Joachim Kunz proved the celebrated Bott periodicity It's one of the most important theorems of the 20th century. Using Teplitz algebras. So remember the name. This is very, very important, and it has so many incarnations. I mean, the way Teplitz was looking at it was completely different. He was looking at appropriate functions on the disk, which have some properties on the down to a circle, and so on and so forth. One could say the whole lecture about Teplitz algebra. I mean, if you look up Wikipedia for Teplitz algebras, this is a 2-hour lecture to explain all this. Okay, I don't want to do it. I just algebra. It's so annoying. When I touch the top of the screen, it reacts not the way I intend to react. But then there was so Teplitz. This is he lived. He died in the 40s during the war, and then there was some fundamental work of Coburn, a very nice person from State University of New York at Buffalo, in the state of New York, and he wrote the seminal papers in which he proved that in fact this completely given, geometrically given Teplitz algebra is in fact nothing else but the universal sister algebra generated by one isometry. Okay, so this gave a very neat algebraic description of this operator algebra. Also, the Teplitz algebra is like one of the prime example of index theorems. This is exactly what you study. If you want to teach students what index theorem is all about, then you start from the Teplitz algebra. Okay? So you look at these operators over there, and you say what an index is, and you don't have a baby but non-trivial version of an index theorem, then you look to it with Teplitz algebra. Another thing which is interesting, this is one of the most recognized short exact sequences of sister algebras, a so-called symbol map. As its name back to geometry, as studied by Teplitz himself, to continuous functions on the circle, and then the kernel is just the sister algebra, the ideal of all compact operators inside. And so that's one of the most popular short exact sequences of sister algebras. If somebody wants to show me a quantum group, then he speaks, well, Voronozh's SQ2, that's like most famous quantum, compact quantum group. If you want to see a short exact sequence of sister algebras, everybody will start from giving you this example. Okay, but for us, you know what happens here? If you forget the completion, right? So here this will be the Levitt-Pav algebra. Sorry, this will be no. Sorry, this will be the con. Sorry, I was wrong. So this will be con Pav algebra of this graph, which is one loop, okay, and this is Levitt-Pav algebra of this graph, which is one loop, okay. So when you complete this, you get Teplitz. When you complete this, you get continuous functions of the circle. So what happens here is that I just have an isometry S star S is equal to 1. Because this is a con Pav algebra, so I impose on the first conspiguration. But when I quotient it to the Levitt, well, I have to impose also the second conspiguration, which is SS star equal to 1. And then my isometry turns into a unitary. And the universal sister algebra denoted by one unitary is what? Continuous function of the circle. Okay. So the little game we are playing here with such a simple diagram, con algebras, late algebras, it actually encapsulates some very, very, very important examples from mathematics, which has nothing to do with graphs. Which shows that this is very useful because it's very important when you have some theory that it has fundamentally interesting examples, and this does, all right? Of course, I was here just hand waving this as a motivation, but see, the goal of this course is when we are done with Leibniz algebras, then we will go into sister conclusions, and we'll consider these guys as graph sister algebras. And this will be a short exact sequence of graph sister algebras. Okay, all of them are graph sister algebras. But at the time being, I can just tell you, all right, we have some conclusions, they exist, and these are the sister algebras. But on the algebraic level, this part you already understand. Right? This part you don't understand. It has this exact sequence. You define the Leibniz algebra as the quotient of the Pond algebra by the ideal generated by the second post-trigger relation. Okay. So here you have only one relation, and here you have two relations. So so the symbol maps the isometry to the unitary. Okay. That's exactly what happens. All right. So I think enough about this example number 3. Now we can go to example number 4. Any questions about the techniques and around polynomial algebras? No. Okay. So example number 4. I have to stay away from the top of the page. Okay, so let it be a little bit more complicated. You can call it some rose petals. I like to call it Hawaiian needle. It's just a question of how you draw it. From the point of view of graphs, that's irrelevant. So I have n loops, E1 to En. This is a Hawaiian nearing way of drawing it, but I can also draw it like this, E1 to En. Putting them inside or outside doesn't matter. So this is Hawaiian. Nearing. And this is rose petals. Okay, this is my graph. So what happens then? Well, again, there's nothing to prove, but there is some interesting history. I know that I'm trying to explain unknown by unknown, but it's very important to understand why these algebras were baptized as Kohn path algebras and Leibniz path algebras. There was a reason. Okay, so for starters, if you look at the Kohn, and again, it doesn't make sense to make the relative because you have only one vertex. There's just one regular vertex. Either you do your relations, the second plus three relations, or you do not. So either you take Kohn or you take Leibniz. There's no fooling around with X. Okay, so you take C, K, where is it? C, K, E. And this is isomorphic with so-called Kohn algebra, not path algebra. Kohn algebra of the signature 1n is a Kohn algebra. So this guy studied these algebras of a certain sort. So I mean, you can write explicitly what these relations are. It's not a big deal. It's very much as with the Tepes, this kind of multi-Tepes case. And for some reason, he was interested in such algebras. Okay. So you have n generators without stars. You have n generators with stars. And you impose that each and every one of them is an isometry. So you have like a bunch of non-commutative isometries. And for some reason he was interested in these algebras, and after his work they're called Kohn algebras. So for this particular graph, okay, E, the Hawaiian nearing graph or rose petals graph, the cone path algebra becomes a cone algebra of signature 1n. And I cannot say anything more about it because I'm not aware of the motivation of this guy. However, when we take the Levitt path algebra of this graph E, this becomes, surprise, surprise, the Levitt algebra of signature 1n. But this I can explain. Because Levitt was interested in the following problem. You see, when you have a commutative ring and you have a free module of a commutative ring, it might not enjoy having a dimension. So you know that when you have a vector space, which is a free module of a field, then of course there is a dimension. Because you have this fundamental theorem, which is quite difficult to prove, that every vector space admits a basis, and a very difficult theorem again, that if you have two different bases of the same vector space, there is a bijection between them. Of course, when you think finite, it's easy, but when this is what you do at first year algebra. But when you think about some, I don't know, crazy vector spaces of uncountable bases, I mean, that's no longer so easy. That is still true. Okay, so every vector space has a dimension. This is not true about modules over rings, of course, non-commutative rings. Okay, so in particular, Levitt was interested in the following problem: what would be like the universal algebra or the universal ring R having the property that free module Rn is isomorphic as a free module with a module Rn, or n different from n. And for a sort of minimal ring which would satisfy this isomorphism of modules, he would call it the Levitt algebra of signature Mn. Okay. So in particular, you can take n equal to 1 and look whether we have a ring with the property that the module Rn as a module is isomorphic with the ring R. And you can see that this Levitt path algebra for this particular graph has this property. You do have it, but if you take L K E to the power n, so just n copies, right? This is a direct sum of n copies of this ring. Then this is indeed isomorphic with Lk E itself. And this is all because of the relation that we enjoy. Of course, we have the relation that EI star EI is equal to 1. All right. But we also have the relation, the second constrictor relation, that says that sum from I equal 1 to n of EI star is equal to 1. And basically, this is what gives this isomorphism. This is what gives this isomorphism. You take an element in here, so E1 up to n times some numbers, I know, lambda 1, lambda n, okay? And you have a scalar product with E1 star dot 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 up to En star. And we apply the scalar product, well, you will get simply the sum of all these lambdas. And you can prove that this is actually a ring, sorry, a modular isomorphism. So this crazy relation, I mean crazy, it looks completely innocuous when you look at it from the point of view of path algebras or graph algebras. But in fact, this is an example of a ring or even an algebra with this crazy property. So in particular, one of the things that you can immediately conclude is that this ring has no finite dimensional representations. Because if this ring had a finite dimensional representation, then you would have that the dimension of the representation on the left-hand side would be n times the dimension of R, the representation of R. So n times some finite number is equal to this finite number. That's impossible for n different from 1 and the dimension different from 0. Okay, we'll have an n times dim is equal to dim. So for of our representation space. So when this is a non-zero number, of course, you can divide by it and you get n equal to 1. So this is an example of a non-commutative ring, which does not agree the finite dimensional representation, and which enjoys this crazy property that you can have 3 modules, but you cannot talk about the dimension of the 3 modules. So if you hear anybody on the street claiming, oh, there is a module of a non-commutative ring and it's a 3 modules, I know its dimension, stop, because the dimension did not exist. Because dimension is defined as the number of elements in your basis, so it must be independent of your choice of a basis, but in this case it isn't. I think there is even an entire book about rings for which 3 modules have no dimension. Okay, but this has some universality property, sort of like the minimal construction of having such a ring which enjoys this crazy isomorphism of modules. Okay, so this is what Levitt studied, and these are Levitt algebras, these LKMN. And now, you know, when you take an arbitrary graph, not necessarily Hawaiian ring, well, then you have Levitt algebra. That's a generalization. Okay. So again, you're nothing to prove. This was just a historical story. And finally, my example number 5, it's something with a question mark. This is a difficult example. I mean, I remember in the previous semester we were sweating to really decipher what is the path algebra for this graph. Okay, and I think that we came to some conclusions, but this was actually quite tough. But it's also very interesting and fundamental. So now I take E to be a graph with a simple path, but now closed into a loop. Okay, so I have yes, say n minus 1 edges. Okay, or n edges, n vertices, whatever. Okay, let me see. If I have if the number of edges is 1, then I should have a 1 by 1 matrix. Okay. So yeah. So let's say that I have n edges. Yeah, and it will be the size of my matrix. Well, then I believe that when you look at the relative, because you see here all vertices are regular. Okay, you have as many vertices as edges, and all these vertices are regular. So now we can play around with the relative compact algebra and choose your x as you please. And now I claim, but I'm not 100% certain that this is the following construction. This is a different mxn of k. So remember this funny modified relative matrix algebra, tensor product over k, of course, with Laurent polynomials. So this is what I conjecture it to be. But let me put a question mark here. With the other example, I didn't write a rigorous proof, but I bet 10,000 euros that this is correct. But here I'm a bit more cautious. I still believe it's true, but well, I would like to see a proof. But it will be an exercise for me. But I have to explain what I mean by the tilde. So here, m tilde and xk differs from the previously defined m and x k by replacing the condition di does not belong to X cap Vn by the condition Vi does not belong to X. Well, this is given in terms which are not graph related, but if you like to write it in terms of graphs, so then though these things mean the same, this means that Vi is the regular vertices of E less X. All right. It's just that when you have a straight path, when the last vertex is not a regular vertex, and you have to separately exclude it. But here all vertices are regular, so we no longer demand that Vi be different from Vn, because Vn is again a regular vertex. Okay. I start from V1, V2, and I come here to Vn. Vn is also a regular vertex. It's not the same here. And I have E1, E2 up to Vn, right? En going from Vn to V1. So that's why you have to make this replacement, and this is what you mean by what is meant by the tilde. But the construction is exactly the same, except that this one condition which defines at which slots we have this unital commutative ring instead of a tilde. I throw out the n. I'm no longer demanding that Vi be different from Vn. It might be it's a regular vertex, and you might choose not to impose the second relations of this n vertex. Okay? And in particular, and this is something we're certain of, because this is well known. We have that the Levi algebra. So if you want C regular E Ke, which is just the Levi algebra of E. This is known to be isomorphic with n by n matrices, tensor product with Laurent polynomials, or you can write it down as Laurent polynomials with coefficients in the matrix. So n and k, and here Laurent. And you can also write it as matrix algebra with entries being Laurent polynomials. Sorry, I need enough space. As I said, n by n matrices, but not over a field, but over the ring of Laurent polynomials. Okay, so this is a fact. For the Levi, it's a fact that if your simple path closes into a loop, then after you do, say, the C-star completion, the graph C-star algebra will be just continuous functions on the circle, but with values in n by n matrices. Okay, so when you complete into the graph C-star algebra, the C-star algebra of non-continuous maps from S1, n by n matrices over complex numbers. Okay, so that's when you complete with the C-star norm and take your first you take your field to be complex numbers, and then you complete with the C-star norm. So that's a fact. This is well known. This is standard, right? But now I wanted to see what happens in the relative version, and the relative version includes also the case when X is the empty set. So this is like this absolute con path algebra, and I believe that it behaves in precisely the same way as in the case when you don't close this simple path into a loop, but you have to make this modification by tilde, because now all vertices are regular. And also you have to make this, and you have to have these Laurent polynomials in addition, right? Roughly speaking, the idea is that once you close the simple path into a loop, what happens is that you treat this loop like your generator of Laurent polynomials, okay? And going with stars, you go in the opposite direction. So this is sort of your unitary, composing all these edges into a loop. You assign to it a certain unitary, and when you take the opposite path, so now you take the start edges going in the opposite direction. This will be the inverse. But that's not enough, because you don't have to just take these full loops. You can go 1 million times around the loop and then 5 steps. So that is finite matrix algebra. But making it rigorous is quite a bit of work. And certainly one has to provide the proof in this relative case. I've never seen it done. So somebody will be lucky to have it as an exercise. I bet it is true, but I'm not certain. I'm certain in this case when X is the set of all regular vertices, which means all vertices. Okay, any questions about this case? Well, we're doing very badly in time. I'm still doing examples, and we didn't even start proving the lemma. Okay, but I still have one more example. Example number 6. So what happens when E is an infinite graph? So it's a simple path of marching off to infinity. Okay. Well, then I believe the answer is the following. For relative cone algebra. This is equal to, I will call the relative infinite matrices. Or how do we construct them? Well, we construct them as follows. This is the union over all non-zero natural numbers. Of what? And here I have to use tilde. So luckily I already explained the tilde before. And the set I'm taking here is X, but intersected with first n vertices. So V1 to Vn. You see, unlike in the case of a finite simple path, all these vertices are regular. I don't have to throw out Vn. You see, Vn is also a regular vertex. So that's why I have to modify this condition, right? I have to say that, I'm modifying things at places which have this property that Vi is not in X cut Vn. No, it's simply not in X. Because all vertices are regular. Okay, that's why I have to put this tilde. And of course it's over. Okay, right? And how do I make sense out of this union? Well, I have to, so these are, if you want, arbitrary signs. But finite matrices. Where I have to make sense out of this union. Well, I have to say how n by n matrices are viewed as n plus 1 by n plus 1 matrices. Well, that's the obvious way. You take this m n tilde xn, okay? You take a matrix like this, and you map it to the following matrix, where here just put n, and everywhere else you put the 0. And I will view it as a matrix of course, size n plus 1 by n plus 1. And you take it's relative to the subsets xn plus 1. And the only thing that you have to demand is that xn is containing xn plus 1. All right, so here these are these modified matrix algebras, but without doing any harm to the last right bottom entry. Okay, it's still a regular vertex, so you still either choose to do multiplications there or we do not choose. And here in in this particular case above, my xn, this is my xn, okay? And of course, my xn plus 1 will be the same thing, but now I will be comma vn plus 1, all right? So obviously they are contained in another one in another, because the set v1 to the n is contained in the set v1 to the n plus 1. And all vertices are equal. So this is where you include n by n matrices in n plus 1 by n plus 1 matrices by this explicit recipe. And you must assume that always xn is contained xn plus 1. So that, you know, when you modify something at diagonal places, you also modify it when you view its matrix as a matrix of a bigger size. Okay, so that's why you have to have this containment over here, right? Because we are saying that we are modifying if vi does not belong to this set. So if it does not belong to xn, so say vi does not belong to xn, so that it might belong to xn plus 1. I'm a bit confused. But it's 0 over here, so we don't care. We don't care. Yeah, and anyway, the idea here is just that if we do some modifications here at slopes, say I, then when I do this I as an element running not from 1 to n, but from 1 to n plus 1, then also here we should have this modification. Okay, and I hope I captured it here. So yeah, because yeah, maybe I shouldn't be so no, let me be slightly less general, because this is a trap. I want to give it to you as a warning. I remember once we published a mistake, because we are over time working with compact outer spaces, and what we claimed was actually true in full generality for all locally compact outer spaces, but I don't know why we decided to write in the introduction, okay, take arbitrary topological spaces, that blah 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 is true. And it turned out that this is not true. That is actually false. Like at this level of generality at which we wrote it, it was actually false. And of course, we didn't need this level of generality. We just worked with compact outer spaces. So I don't want to make the same mistake. So where's the eraser? Where's the eraser? Yeah, here. And no, I'll just, instead of demanding such a thing, I will simply, this is my definition. You see, this is my definition of xn. I'm not considering other cases. This is the definition of xn. Okay. So that if I am not if I have an element I, which is first ranges from 1 to n, okay, and is not in xn, then it's also not in xn plus 1, right? Why? Because the only thing that can happen is if I take xn plus 1, all right? So xn plus 1 is either equal just to xn, or in which case it's true, or xn plus 1, there are two cases, is equal to xn union vn plus 1. Okay. there is two cases. But because I assume that I is from 1 to n, saying that Vi is not in xn plus xn plus 1 with this definition of xn, with this case of what xn might be, then of course it means that it is not in xn and it's not Vn plus 1, but it's by assumption of Vn plus 1. So that's correct. My intuition was correct, but I tried to generalize it too much. So I have this inclusion, but that's my definition. X is some fixed subset of natural numbers, if you want, or vertices labeled by natural numbers belong to infinity. And when I jump from xn to xn plus 1, this is precisely this way. I hope I made it clear. Yeah. Any questions? No. So now let's look at a particular case. So in particular, for x being the whole E naught, everything, I get the Levi path algebra. I have, if you want, C, K, E naught of E, just the limits of algebra of E, and then this is equal to the usual algebra of arbitrary size finite matrices. Okay, that's the standard thing which everybody knows. And again, when I take my x to be everything, you see, then if you look at this definition, then all these xn's are also everything. So basically, I'm saying that Vi is not in xn. I'm saying that simply there is no Vi. So I modify it nowhere. So I'm just getting regular n by n matrices over my field K, and I put them in the standard way one into another. Yeah. If I want to view a matrix n by n as a matrix n plus 1 by n plus 1, I pad it with zeros around, so that m is just in the left upper corner of this n plus 1 by n plus 1 creature. Okay, so that's this is my sixth and final example. However, one more comment is due. So how about completions? So in other words, how about the C-star completion of this? The C-star completion of n infinity C. Well, this is the famous C-star algebra of compact operators. So this is a very, very, very important C-star algebra. That's precisely how you should think about it. But the C-star algebra is the norm closure of finite matrices. So in other words, what happens when you take the norm closure? Well, you have to assume that when you look at entries of your finite matrices, well, now your matrix can be infinite. It no longer needs to be finite. But these entries will have to go with norm to 0 in the right way. Okay. So that's this is like having functions vanishing in infinity, right? When you have a compact space, say like the circle, then any continuous function is bounded because the space is compact. But you have a real line. Well, if you have a C-star algebra, then you must have a function vanishes at infinity. Okay. So here's a similar effect. You no longer have to require that the size of a matrix is finite. Okay, you take the norm completion, but you have to, in the right way, make sense out of what it means to have the C-star completion, and it, roughly speaking, says that these entries, when you run to infinity in whatever direction, they go to zero in appropriate way. Okay. So that's a very, very important sister algebra. It's also a simple ideal. It doesn't have any closed ideals inside. That's a very important property of compound operators. And now you understand what we meant where we're talking about the kernel in this celebrated Schrödinger sequence. You see, that's exactly the sister algebra which I put here. And I dare say that when I look at the kernel here, simply the kernel of this map, so let's call this map to sigma and call it the kernel of sigma, then I dare say that this is precisely the algebra generated by so what will it be? So it will be the length of algebra that of such an infinite path. So that's somehow a funny picture that you get here. And I'm not exactly sure how to show it, because I only know that this is true on the level of taking sister completions. So I'm writing it with a question mark, but it definitely should be the algebra of finite rank matrices, arbitrary finite rank matrices. And yeah, that should be precisely the kernel here. Yeah, and then it is indeed this Levy-Cohen algebra. But this has to be verified. Okay, we have 3 minutes left, so it doesn't make sense really to start a new topic. We are done with examples. Let me ask one more time. Have you got any questions? No. Okay, so at least let me advertise before the break what it is that we are going to start the next lecture from. Namely, to prove that the identifications in our examples are correct. I mean, except for some simple cases when just debating history of Kohn algebras and Levitt algebras and just have one loop. I mean, then things are known, right? Step-lit algebras, Laurent polynomial algebras. There is nothing to prove. But the moment you go to this relative business, yes, there is something to prove. You see, so this case with one vertex only is simpler, right? Because either you do Kohn or you do Levitt. You don't have anything relevant. But when you go to this relative business, well, then I did my best to compute it, but it has to be proven. And you cannot prove it, I repeat it. We have time today, you cannot prove it without having a basis theorem. And for starters, we have a basis theorem just for Kohn algebras. Okay, so this will be a lemma which we have to prove next week. So let E be a graph and K be a field. So no surprise here. Then the set, and this is a very important set. Let me denote it as calligraphic G E, and I define it as follows. I have these Kohn classes. Remember, Kohn algebra is a particular quotient of the path algebra of extended graph by some ideal. So I denote by the squared brackets the equivalence classes of elements in the path algebra of extended graph. And here I put chi, alpha, beta star, under the assumption that the end of the path alpha is equal to the end of the path beta, which, as you should remember, is equal to the beginning of a path beta star. So alpha beta star is non-zero. I mean, chi alpha beta star is non-zero. And this is over all alpha betas in FPE. So take all finite paths in the graph. So take this set, okay, and I claim that this set is a basis CKE. Okay, so this is the absolute Kohn algebra, but in total generality, E is any graph. And surprisingly enough, it's quite a lengthy combinatorial calculation. It's trivial. I mean, it's completely automatic. There is no trick, no deep idea, just basic algebra, but you have to verify a certain associativity condition, which is well, quite demanding combinatorics. And I spent the whole night checking it, and now I didn't have time to say it. So this is how it happens. Anyway, let's have a break and resume with recitation class at 4:15. I stop recording. I stop sharing and stop recording.